Okay, welcome back. Here we are again. You can see I've done a little work since I stopped the last video. And the example we just did was an example that you'd see measuring on something like a ruler. There are also devices used for measuring very commonly in science labs known as graduated cylinders, and they're used for measuring volumes. They're basically like measuring cups in the kitchen, but more accurate. And when you're measuring a volume in a graduated cylinder, you often have to do some estimating also. One of the problems with measuring in the graduated cylinder is what's known as the meniscus. meniscus, and that is a curve in the surface of the water that's caused by the fact that the water is actually attracted to the glass that the graduated cylinder is made from, and it's trying to crawl up the sides, and therefore it's lower in the middle because there's nothing there that it's attracted to. In order to measure the volume of water in a graduated cylinder, the graduated cylinder generally needs to be tall and thin in order to get an accurate volume, because when the container is tall and thin, a small difference in volume will make a big difference in the height. And so basically the taller and skinnier a graduated cylinder is, the more accurate it is at measuring volumes. But unfortunately, the taller and skinnier it is, the more pronounced the meniscus gets also. So in order to get an accurate reading of a volume from a graduated cylinder or similar measuring device, you have to find a point somewhere on this curve that you can measure from and do it reliably and reproducibly, and get, basically that you and other people measuring from that spot would get the same number over and over and over again, for the minimum error. And they have found through many years of investigation that the best spot to use on the meniscus for measurement is the very bottom of the meniscus. Not the top, not the bottom of the top, not the top of the top or the top of the bottom or anything like that. Bottom of the bottom, that's the best place to use. Okay, so that brings us to a measurement that would be right there. In order to do this, it's best if your eye is on the same level as the liquid in the graduated cylinder. So you might have to hold the graduated cylinder up if you have a steady hand, or you could put it on a shelf and look at it if you can't hold it still enough, and look at it that way, and that way you get the most accurate direct on angle for the volume. Now, in order to measure this volume, we can see that it's greater than 15 milliliters, but less than 16 milliliters. So right away we know that the volume is going to be 15 point something in milliliters. And if we count the smaller markings between 15 and 16, we see that there are 10 of them, which means those markings are 0.1 milliliters each. We can see that the line is above 15.1, and it's above 15.2, but it's less than 15.3. So we know the next digit is going to be 0.2. And we don't want to just leave it at that, because clearly it's not exactly 0.2. It's 15.2 something. We can look at it and see that it's most of the way between 2 and 3, but not all of the way. And we have to basically estimate. So it looks to me like it's maybe 70% of the way between 0.2 and 0.3, which means your last digit would be 7 milliliters. 15.27 milliliters, that would be my best guess for what that volume right there is. And since we assume that the last digit is uncertain by plus or minus 1, that would mean that this volume is actually 15.27 plus or minus 0.01. So that allows the last digit to vary by plus or minus 1. What that means is that this volume is actually somewhere between 15.26 and 15.28 milliliters. And that leaves some room for disagreement. If you looked at that line and said, no, it looks like it's more like 80% of the way between 0.2 and 0.3, I could say, yeah, it could be, because that's within the range of possible values. Even though we end up with a range of possible values from this measurement, it is definitely more accurate than just leaving it at 15.2, because that would imply that it's 15.2 exactly, or in other words, 15.20, and it was clearly not that. Okay, so this, but basically you want to estimate one place beyond the smallest markings on the measuring device. It's a fact that all measuring devices have some degree of uncertainty. And some of the things that contribute to uncertainty would be things like the sharpness of your eyesight, the clearness and sharpness of the lines on the measuring device, the thickness of the lines on the measuring device, the accuracy of the lines on the measuring device. We kind of take it on faith that a ruler has been calibrated and that the markings on it are actually accurate, reasonably anyway, but they're probably, they're probably not 100.00000% accurate. They're probably at least a little bit off. Okay, so yeah, that's the problem. And when it comes right down to it, the number of digits in the number are related to the accuracy of the measurement. And so we had 4 digits in each of these measurements, and that implies that we actually knew those measurements fairly accurately. If it were just, say, 15 milliliters, that's clearly not a very accurate measurement. This brings us to the idea of significant figures. Sometimes known as sig figs or just SF for short. Significant figures are related to the accuracy of measurement. And a significant figure would be a digit that comes directly from the measuring device. Okay. In a lot of cases, it's easy to figure out how many significant figures a number has. And in quite a few cases, it's not so easy. The problem is the zeros. Because there are rules for counting significant figures. And some of these rules really make sense, and others you might have to work at remembering. And the reason that we might want to count the number of significant figures in a number is that we, well, like we said, it's related to the accuracy of a measurement. So knowing how many significant figures there are gives you some idea as to how accurate the measurement is. And also there are other rules that govern how many significant figures the result of a calculation is allowed to have based on the number of significant figures of the numbers that go into that calculation. Because the number of significant figures in a number is related to the accuracy with which you know that number, you have to be very careful about significant figures when you're doing calculations. Because if you, say, do a calculation involving one number that's really, really accurately known and one number that is not very accurately known, you don't want to imply that you know the result really, really accurately. Because of that one number that you don't know very accurately, that means that the result of any calculation involving that number cannot be known very accurately. And if you're watching significant figures, the significant figures in your answer will reflect that. Okay, you don't want to pretend that you know a number with greater accuracy than you really do. Okay, so the rules for counting significant figures are as follows. Okay, first of all, non-zero digits are always significant. So that means any number other than a zero is significant. The zeros are the troublemakers. If the zeros come at the beginning of a number, they are not significant. All right. If the zeros come between other numbers that are not zeros, then they are significant. And and zeros at the end of a number. Now this gets even more fun. Zeros at the end of a number are significant if there is a decimal point, but if there's no decimal point, zeros at the end of a number are not significant. Okay, so just to recap, non-zero digits are always significant. Zeros at the beginning of a number, that is over on the left-hand side, are never significant. Zeros between non-zero digits are always significant. Zeros at the end of a number are significant if there's a decimal point, but not significant if there's no decimal point. Okay. The rules for counting significant figures given in the math handout are a little more complicated than what I wrote out here. Whoops, what I wrote out here. And so you can look at those and you can use whichever set of rules you like because they will lead to the same result. I think that my system is a little more simple and easier to remember, but if you like the way that it's presented in the math handout, you can use that system too. So no problem. Some examples, there are some examples here in the math handout. Okay. This is on the page that's marked rules for determining the number of significant figures in a measurement. And on the left column, you have value of the value of the measurement and number of significant figures in the right-hand column. The first number is 1,000 with a decimal point at the end. The number of significant figures for that, well, it would be 4, actually, because remember, zeros at the end of a number count if there's a decimal point. So those 3 zeros count as significant along with the 1, so that's 4 digits altogether. If you had 1,000 with no decimal point, this is not on the table, but I'm just adding it in now for comparison, how many significant figures would there be? Notice there's no decimal point. That means zeros at the end of the number are not significant. So this only has 1 significant figure. Technically, it's ambiguous. I mean, it could be 1 or 2 or 3 or 4, but to be on the safe side, we usually assume the smallest number of significant figures possible when it's ambiguous. Okay, so we'll call it 1. The next number on the table is 45.0, and again, zeros at the end of the number are significant if there's a decimal point, so that would be 3. The 4 and the 5 are obviously significant, as is the 0 at the end. We've got 1.02. There is a decimal point, but that doesn't matter because the 0 is actually between non-zero digits, so it is significant. So that would also be 3 significant figures. Under number 2, yeah, these rules are pretty complicated as they're listed here in the math handout. You might want to use my rules. Anyway, the value of the measurement under number 2, the first one is 12,000. No decimal point. That means the zeros at the end are not significant. So that's only 2 significant figures. And then the next one is 405,300. Notice that there's no decimal point, so the zeros at the end of the number are not significant, but there's another 0 that's between 2 numbers that are not zeros, so that is significant. So 1, 2, 3, 4. 4 significant figures. 60 with no decimal point would be 1 significant figure because the 0 at the end, not significant. Under number 3, we have 0.000278. Remember that zeros at the beginning of a number are never significant, so none of these zeros counts as significant. They're important because they locate the decimal point, but that's the only reason they're there. They're not products of measurement. So the 2 and the 7 and the 8 are from measurement. And so there are 3 significant figures there. If you had 0.0120, there are 2 different types of zeros here also. There's the one at the end, which is significant because there's a decimal point. The decimal point does not have to be right next to the zeros at the end. It can be way at the other end of the number. If there's a decimal point anywhere in the number, then zeros at the end are significant. But zeros at the beginning of a number are never significant. So it's just that 0 at the end plus the 1 and the 2 for 3 significant figures. Okay. And like I said, the main point of being able to count up how many significant figures there are, and we'll do more examples of counting up significant figures as time goes on here. But the main point of being able to calculate or count up the number of significant figures in a number would be for the purpose of calculations, because you need to know how many significant figures are in all of the numbers that go into a calculation, so that you won't give the impression that you know the answer to the calculation more accurately than you really do. Okay. Okay, so to put that in writing, the least accurately known input number, that is the numbers that go into a calculation, that's what controls how accurately we can know the result of the calculation. And so the essentially the number with the fewest significant figures, that determines how many significant figures you can have in your answer. Okay. So the rules, again, I'm going to state the rules a little bit differently than they're stated in the math handout. And you can read over what's in the math handout, and if that makes more sense to you, then go with that. Otherwise, you can go with my explanation. And, either way, it'll lead you to the same result. So it doesn't really matter which way you go or which system you follow. So the rules for calculations are divided up between addition and subtraction and multiplication and division. Addition and subtraction, when you're doing addition and subtraction with numbers, you're actually more concerned about you're more concerned about decimal spaces. That is, the spaces after the decimal point. And so the rule is that the input number, that is the number going into the calculation with the fewest decimal spaces, controls the number of decimal spaces in the answer. So just to make up an answer out of thin air. So say 52.069 centimeters plus 71.1 centimeters plus 26.00395 centimeters. When you add all of those numbers up, what would your result be? Well, if I do this on my calculator, and I just made that up, so I'm going to have to do it on my calculator, 52.069 plus 71.1 plus 26.00395 gives me 149.17295. And that would be centimeters. The problem is that when you look at these numbers, you see a whole different range of numbers of decimal spaces. The first number there has 3 decimal spaces. So what that means is we know this number to the nearest thousandth of a centimeter. The second number only has 1 decimal space. We only know that number to the nearest tenth of a centimeter. And then this last one has, wow, that's a lot. 1, 2, 3, 4, 5. So we know this number to the nearest 10,000th of a centimeter. We're adding these 3 numbers together, 2 numbers that we know pretty accurately, and 1 number that we don't know very accurately. The one we don't know very accurately is going to control how accurately we can possibly know the answer. So this answer is only allowed to have 1 decimal space. Okay, so we're going to have to round it off. So that it has 1 decimal space. The first decimal space is the 1, and that means everything after that has to go. When you're rounding numbers off, though, you have to look at the first number that's being dropped. If the first number that's being dropped is 5 or greater, then you have to round up the last number that's being kept. 7 is greater than 5, so that 0.1 has to become a 0.2. And so that is the correct answer with the correct number of significant figures in it. All that other stuff, the 7295, those are digits that we didn't really know. And the problem is that most I'm not aware of any scientific calculators that know anything about significant figures. They will spit out an answer as if, all the digits after the last one you put in are 0. So this 71.1, the calculator treats that as 71.1000000 on to infinity, because it doesn't know any better. And so basically it's up to us to realize that those aren't all zeros after that number. That's 71.1, because that's all the accuracy we know it with. We don't know that number very accurately. And so it's up to us to recognize that we have to cut the answer down to the right number of significant figures, or the right number of decimal places if you're adding or subtracting. Now, if you're doing a multiple step calculation, that is, if you're going to take these numbers and then maybe take them and multiply them by something else, then you don't have to round off until the final step. You do want to avoid rounding off too often. So for any given calculation, you should only round off the number once at the very end of the calculation. Okay, the other type of calculation, it would generally be multiplication and division. Multiplication and division are where we are concerned with total number of significant figures. So again, you don't want to give the impression that you know the answer of a calculation more accurately than you really do. So you have to count up the total number of significant figures in the numbers and round the number off so that it has the same number of significant figures as the input number with the least significant figures. And so you want the answer to have the same number of total significant figures as the input number with the least significant figures. Okay, so if we have 35 inches times 76,485 inches, and you multiply those together, you get so that would be what, 2,676,975 square inches. Remember, actually, I don't recall if I've mentioned it yet or not. When multiplying and dividing, you treat units as if they were numbers. So if you have inches times inches, that's equivalent to inches to the second power, or in other words, square inches for the unit. Okay, this number, though, has a grossly excessive number of significant figures. If you look at the numbers that went into that, we have 35, which only has 2 significant figures, and then we have the 76,485, which has 5 significant figures. This number here has 1, 2, 3, 4, 5, 6, 7 significant figures. That's obviously way too many. What we have to do is cut it down to 2. So we take the first 2 significant figures, which would be the 2 and the 6, and we have to drop everything else. Okay, so we're going to change this to a number with 2 significant figures. The 2 and the 6 can stay, but everything else has to go. But again, look at the first number that you're dropping. It's a 7, which is greater than 5, so the last number you're keeping has to go up by 1. So we have 2, 7. Now, you're not done yet, though, because obviously 2,676,975 does not round off to 27. If the numbers that you drop are before the decimal point, then you have to fill in those spaces with zeros in order to maintain the magnitude of the number. So we dropped 1, 2, 3, 4, 5 numbers before the decimal point. So we need 5 zeros. That maintains the magnitude of the number. So 2,676,975 does indeed round off to 2,700,000, which is what this number is. And that would be square inches. Okay, so that's kind of a quick review of significant figures in calculations. And we'll do some more examples as time goes on. Let's see. There is an example, say, so what would be the speed of a ball that travels 8 meters in 4 seconds? And we haven't really covered speed yet. We will do that in the future. But speed would be basically distance divided by time. So the distance traveled is 8 meters. Divided by the time, 4 seconds. And that would be units of meters per second. And the number would be 2.0. Now, if you take 8.0 divided by 4.0, your calculator is almost certainly going to tell you just 2. But while it's certainly important to avoid using too many significant figures in your answer, it's also important to avoid using too few. So just 2, that's only 1 significant figure. you have division between a number with two significant figures and another number with two significant figures. So that means your answer should have two significant figures. And so if even though your calculator tells you 2, you want to make it 2 with two significant figures, and the only way to do that is to call it 2.0. Okay. Sorry. Okay, so okay, there is a page right after this called Significant Figures Worksheet number 1. And we can go over these together here. And we'll look at the certain measurements and the number of significant figures. And the third column is rule applied. And to me, it's not really that important which rule you're applying. I mean, what number of the rule that you're applying is. I don't care what number it is, as long as it's the correct rule and you apply it correctly. That's the important thing. So you don't have to know the numbers of the rules. Just know what the rules are and how to use them. So I'm not going to do the third column. I'm going to skip that. Okay, so the measure the measurement is 0.0380, which sounds familiar. Have we seen that before? I don't know, maybe not. Anyway, significant figures. We've got some zeros at the beginning, but remember, zeros at the beginning never count. We've got a 3 and an 8, and non-zero numbers always count. And then we've got a 0 at the end. To find out whether the 0 at the end counts, you have to look through the numbers to see if there's a decimal point. If there is, then it does count. And there is, and therefore it does count. So there are 3 significant figures in that number. $75,000. Obviously, like I said, it's the zeros that are the troublemakers. So you want to look for zeros because they're the ones that are going to give you trouble. And the 7 and the 5 definitely count, but what about the zeros? Well, that right there is that little dot there, that's a smudge. That's not a decimal point. So this number has no decimal point, so those zeros at the end do not count. That's 2 significant figures. Oh, and the unit was meters. 25.8 liters. That's an easy one. There are no zeros in it, so all the numbers count. So that's 3. 6,005 square centimeters. And the zeros in this case are between non-zero digits, so they both count. So that's 4 significant figures. Remember, when I said the zeros between non-zero digits, I didn't mean that there had to be a non-zero digit directly on both sides of the 0. There could be a couple of zeros in a row. As long as there are non-zero digits on both sides of the zeros, like somewhere before and somewhere after, then they count as significant figures. So both of those count. And let's see, finally we have 75,000 with a decimal point meters. The fact that there is a decimal point means that the zeros at the end do count. So that's 1, 2, 3, plus the 5 and the 7, that's 5. Okay. And so now we want to round these following numbers to 2 significant figures. So we have the original numbers and the rounded numbers. If the number is 0.006539, notice that the zeros at the beginning of the number do not count. So the first 2 significant figures in this number would be the 6 and the 5. The 3 and the 9 can be dropped, but before dropping it, you should look at the first number being dropped. In this case, it's a 3, which is less than 5, and that means that the last number being kept can remain the same. This number is less than 1. So, and the numbers that are being dropped come after the decimal point. So we don't fill in with zeros. So again, the rule is that if the dropped digits come before the decimal point, then you have to fill in the empty spaces in with zeros to maintain the magnitude of the number. But if the dropped numbers come after the decimal point, then you don't need to fill in with zeros. We also have 0.000959 seconds. And again, the zeros at the beginning don't count. The 9 and the 5 are the first 2 significant figures. That means, and everything after that has to go. The first digit we're dropping is a 9. That's greater than 5. And so the last digit we're keeping has to go up by 1. This would be 0.00096 seconds. A number like 647 has 3 significant figures. The only way to get that down to 2 significant figures, well, would be to drop the 7. The 6 and the 4 can stay. The 7 has to go. Again, 7 is greater than 5, so the last number you're keeping has to go up by 1. And remember that the 7 came before the decimal point. Now, in some cases, like numbers like this, you might have to sort of draw the decimal point in yourself, because a lot of numbers, big numbers that are greater than 1 are often, if they're whole numbers, they're often written without the decimal point. So the decimal point is right there. So you do have to fill in that 0. Okay. So that maintains the magnitude of the number. Obviously, 647 does not round off to 65. Those are numbers of 2 very different magnitudes. Okay, 82,500 meters. The 8 and the 2 are the first 2 significant figures. The 5 and the 0 have to go. The first number you're dropping is a 5, so that means the last number you're keeping has to go up by 1. And since the implied decimal point is at the end of the number, you have to fill in all of those empty spaces with zeros. So it's 83,000. And if you have 532 meters, and you want to cut that down to 2 significant figures, then obviously the 5 and the 3 can stay, but the 2 has to go. Again, the 2 is less than 5 in this case, so you don't have to change the 3. But because the 2 is in front of the decimal point, you do have to replace it with a 0. So 530. Don't put a decimal point on the new number, though, because 530 point is actually 3 significant figures. 530 with no decimal point, that's 2 significant figures. Okay. That seems to be about the time limit on this part of the video, so I'm going to stop there, and we'll continue on there from next time in the second lecture. Okay, so until then, see ya.